All right, so for this problem, we're asked to fill in the blanks for this three-step reaction scheme. And right off the bat, I just want to say that if someone says they look at this and instantly know the answers, they're lying. You're going to have to do some problem solving with this. Of course, as we do more and more of these problems, you'll be able to identify the patterns better, but it really just builds off of that foundation we started developing in the first half of the class with all these electronic structures and trends. We're going to use that and apply it to this to end up piecing this puzzle basically together. And that being said, it really is like a puzzle. We can work from the reactants to the products, or the products to the reactants, or even from the middle. Wherever you see a clue is basically a good place to start, and then we kind of just piece everything together from there. So in terms of these clues, I see some at the end and in the middle. Right now I'll start in the middle just because it looks like we're just directly given an electrophile and a nucleophile here. I see my electrophile with a good leaving group here, that OTS, and then I see this NABR here, which will end up being our nucleophile. So the first thing I do is just start by labeling everything we know for this little middle section. We'll ignore everything else for now. We're just trying to get to this intermediate A here, just to start off. So what I can see, if I zoom in the middle, is our electrophile leaving group. If we're trying to determine the substitution of this would end up being connected to 2 carbons, so we're going to be at a secondary position here. And then looking at my NABR now, what I'll find is that when I put this into my acetone solvent, this NABR is just going to split in half, and I'm going to have Na+, just that counter ion that sits there, does nothing, and my Br-. And what we know about nucleophiles is that they have that negatively charged lone pair that we want. So I know that this Br is a fair game and is most likely my nucleophile in this reaction. So I'm just going to go ahead, put the lone pairs and negative charge around this Br. I prepared ahead with that copy paste. So when I am looking at this now, I know that this bromine, yes, we've seen it as a good leaving group. It has a very stable shell around it. It has that bigger radius down the column. So this kind of connects to what we thought as before as a stable conjugate base when we were talking about those conjugate bases. Any bigger radius is going to be able to spread that charge out better and distribute it to just be happier and more stable. So I know that this is going to be definitely a weak base. So I'm going to write that here. And then in terms of being a nucleophile, I know that we've talked about nucleophiles having that negatively charged lone pair, and I see that negative charge on the bromine with all these lone pairs, so I know this is going to be a good nucleophile. So again, the good nucleophile comes from the fact that we have that negative charge here, and then the weak base is just because this bromine has a giant radius, it'll be able to stabilize all these lone pairs better. So, knowing I have a good nucleophile, weak base, and a secondary electrophile, if I pair those together, I am going to end up getting, I have the chart down here too just for reference, I'm going to end up getting SN2 to occur. So we can just go ahead and do that SN2 reaction. I'm going to write it here as well, what we'll end up getting. So I'm going to write here, SN2. And again, the acetone is just the solvent. It's polar aprotic, so it's not going to interact with this negative charge on the bromine. So that's just a fair fit for the solvent. Of course, it's not going to influence the type of reaction. It'll just make SN2 go quicker. So you could technically just ignore that if you want. It's not going to influence our product we get for A here. So when it comes to SN2, we know that doing this mechanism, the main thing you should think is, okay, SN2, its main characteristic is going to be inversion. So I'm going to end up, when I draw out A, I'm going to have to invert this stereocenter here, that alpha carbon. I'll write that as well, I might as well. So when I have bromine attack at that alpha carbon, kick the OTS off. By the way, you don't need to show air pushing for these types of questions, even on the exam, unless she asks for it. Ultimately, we just want what we have in the blanks here as our answers. So I won't draw the arrow pushing just so this doesn't get too complicated looking. But when I do my inversion, when I draw this molecule A now, this intermediate here, I'm going to draw it down here. Everything will stay the same except for that stereocenter. So I will end up getting my H and OTS are basically going to flip places. Of course, we can go through the whole process of having that leaving group OTS leave, shifting, let's say, the H into that dashed spot, and then putting the BR into that empty spot, that wedge we see there that would be missing. But if you want, just to do this a little quicker, you can just simply flip these two groups here and you'll be good to go. Right now, I can just draw my H. It's wedged right now. It'll become dashed on this intermediate here. And then for my bromine that will substitute there, that now will be wedged. So you can kind of see I just flipped this wedge and dash here. That's how we know an inversion occurred in this case. And this would be our intermediate A. So now, I guess what we can do is work from the back and kind of do some like retrosynthesis here to get to this intermediate we just formed. So the first thing I'm going to notice about this third step, if I'm looking at this new molecule we have as our final product, what I'm going to see is, okay, we're still at this secondary position here. Nothing changed about that. It's still our alpha carbon. I'll label it here as well just to be consistent. And I'm noticing that the only thing that looks different right now is I have this new sulfur group connected to my alpha carbon here. And what I'm noticing as well is that it looks like this new group here and this bromine we previously attached, they kind of switch places, right? This one was wedged and now we're going to a dash again. So this is a kind of a hint that an inversion most likely occurred for this as well. So before we get into sorting all that out, because it's kind of a lot, I know, we'll just write down what we know again. That's always your best chance at kind of figuring out what exactly is going on here. So I'm going to say it looks like we had in the single step from A to this final product, we had a sulfur nucleophile. And just looking at this, there's a chance that it probably looked like this. S minus, ooh, actually, sweet. And obviously that's not going to have that many lone pairs. So it most likely looked like this. What's really quick, just to kind of divert for a second, what's making me think it wasn't this is that I know I went from A to this in one step. If I had this attack for step 3, that would mean my product here would still have this hydrogen attached to it. I'd basically have something that looks like this. I'll erase this after I'm done, but I'd have something that looks like this. And I know that obviously I don't have that there. I would need an extra little acid-base situation to finally get to the final product and neutralize that charge. So that's kind of telling me, okay, it must have been a charged sulfur then with no H on it, because that would bring about that extra acid-base step. And I know I don't want that. I'm actually going to redraw this as well, just to make it a little bigger. All right. So now that we determined it's going to be that charged sulfur by this connection pattern we see here, and by the fact that this was just one step, I'm going to kind of recall what type of nucleophile that this charged sulfur is. Of course, we can go look at the nucleophile chart. I put that below. I'll go to it in a second, but we can kind of think through this conceptually. What we're going to find when looking at this negatively charged sulfur is that we have the negative charge lone pair that we need to be considered a good nucleophile. And also, if we think about it in the sense of its basicity then, we know that sulfur is a little bit down the column compared to oxygen, which is right above it. So we're going to have that slightly larger radius that we need to stabilize these 6 electrons a little bit better. So with that extra stabilization comes the classification of this whole thing as a good nucleophile, but a weak base as a result of that larger radius around this. So I'm going to write this here. So I'll say this makes it a good nucleophile, that negative charge lone pair. But the larger radius makes it a weaker base. And again, we can look at that nucleophile chart down below just to make sure. And we find that it ends up being in this box here. And it is actually right here. So again, it's charged, so it has that good nucleophile type of characteristic we need, but that larger radius just stabilizes the charge a little better, rendering it basically a weak base. Now that we have that classification, I'm going to kind of consider what reaction could have happened if we potentially had this sulfur by this step 3 here. And as a little side note, I know that this sulfur has those 2 carbons connected to it here because I see those 2 carbons connected to it in our final product, just as a side note. And I'll actually label that too, just so it's clear. So considering what would happen if I put this good nucleophile weak base with my molecule A that we drew out previously, I'm going to find that I'm also going to get, that won't get smaller. I'm going to also get an SN2 reaction to occur. So again, just to kind of overview what we just did, first I worked backwards and saw what this new addition was in terms of what type of nucleophile and base it was. Then I kind of had to think back and say, okay, if I have this good nucleophile weak base paired with this molecule A here, that secondary electrophile, what exactly is going to happen? It would be SN2, and as a result, we would get inversion. And the fact that we see this inversion occur here at this stereo center just even further guarantees that, okay, we're in the right place. This must be our answer here. So, actually, I put this down here, the questions. So I think this was for step 3, what we're going to look at is anything with that charged sulfur connected to those 2 carbons that we need. So obviously, this is not a charged sulfur here. We have many other sulfurs. This one is not sulfur. This is actually an oxygen nucleophile. This is just a really, really poor nucleophile right here. And again, this all connects back to this chart. I'm going to zoom out for a second. Technically, this, just to kind of be thorough, this here would be considered a poor nucleophile weak base. That would most likely not even react with molecule A that we drew out. Down here, this would react, but it would end up being a strong nucleophile, strong base. So we would end up getting E2 to occur instead. And obviously we see that this is not an E2 product here. So that's also another indicator that we're on the right track with crossing this out here. Now I have to consider these other sulfur nucleophiles here. So I know, I see the answer, but I want to go through the other ones first. So I see here we have this neutral sulfur, which could definitely be an answer. I mean, neutral sulfur is also a good nucleophile weak base that would end up SN2ing with a secondary electrophile. But again, we need a carbon chain connected to it based on the carbons we see here. So I could cross out any sulfur connected to an H. And that leaves us with this as our answer here. I'm going to go ahead and highlight it, actually. Leaves us as that with our answer. And we can kind of see here, this would split in solution. That would just be the counter ion of sodium. And we'd be left with S minus connected to those two carbons that we need. So we're basically done now with step 3 and our molecule A. Now, all we have to do is step 1. So this is actually going to deal with what we did on Monday. And really quick, before I even get into this, I want to write out basically like at its core what Monday was. I know there were so many arrows. Of course, it's fair game for like something to be tested on, but all that you really, really need to know is this. So I'll write it right here. So when we want to go from an alcohol, we'll say ROH for this, alcohol to some sort of good leaving group, we have options to do inversion at that stereocenter that the OH is on. And our inversion reagents for this would be either PBr3, or we can do PCl3. Both of these are basically the same thing. And so is this, SOCl2 plus pyridine. These will let you invert the stereocenter that the alcohol is on. For retention, we're going to deal with any sulfonyl chlorides. And our options for this are, there's 3 of them. We either have TSCl plus pyridine, MSCl plus pyridine, or we have TFOTF plus pyridine. Kind of thinking about what could have possibly happened here now. I noticed that, of course, this is a terrible leaving group. So I want to make it into something better. And to do that, I can just kind of see here that we have this OTS attached as our good leaving group. But I'm also seeing that these dashes stayed exactly the same. So when you think, okay, was this inversion or retention at this step here? Well, it's going to be retention. We didn't change the fact that the groups we're dealing with are dashed. If I see OTS, basically, it's kind of just something you have to remember. Your reagent for this, because we have retention, the reagent would be TSCl, tosyl chloride with pyridine. I'm just going to do that, actually. I'll just say and pyridine. All these kind of come together to, complete the pieces of the puzzle. We identified this was TSCl and pyridine, so that should be somewhere in here. And it is. It is right here. And just to overview, just to be thorough, I know it can't be NaOH. That would not do anything in here. It would probably just remove this tiny H in like an acid-base type of reaction, and that would be it. Like, I wouldn't really do anything. For these two here, this is also another... Yeah, that actually, I don't even think this would do anything. We didn't even talk about what I'm crossing out right now in class. They're just kind of giving you random stuff. Like, the stuff I'm crossing out now, just a bunch of random nucleophiles. Actually, this one wasn't even a nucleophile. That was like its own molecule, it seemed like an ether or something. For SOCl2 pyridine, this one is more of like something you'd see on an exam. Of course, it's one of our alkyl activation reagents that does inversion. But obviously, like we said before, there was no inversion at the stereocenter based on the fact that these are still both dashed. So obviously that also wouldn't be an option. Ultimately, though, these would be our answers for this. What I highlighted, part 1 and part 3. For the A reagent here, it would be this molecule here that I have right below. I'll put like a box around it. And that would get you the correct answers for this problem.